Okay, hi everyone, thanks for coming. My name's Juan, and Prithvi's down there. This is the Jaeger dive session. So both me and Prithvi and I are software engineers at Uber, and more importantly, we're both maintainers of the Jaeger project. So before we get started, how many people here have actually used Jaeger? Okay. I'm not sure why there are so many people at the deep dive. Okay, cool. So here's a brief overview of the agenda. So hopefully a majority of you attended the introduction to Jaeger yesterday. So we'll go ahead and skip the demo and start with the architecture. Then we'll look at how you can tune the performance of Jaeger and gain observability into it. Then Prithvi will go into detail over the new Jaeger features, look at our roadmap, and then cover some administrative topics. We'll try to get through these as quickly as possible to leave time for a lot of questions. Okay, so let's just jog our memory and recall why we need distributed tracing in the first place. So firstly, rather than monitoring individual components of the architecture, like you can with metrics and logs, we can use distributed tracing to monitor distributed transactions across multiple components. Additionally, we can use traces to do root cause analysis, which is integral for companies like Uber, where sometimes a request can fan out and hit hundreds of different services. We can also use traces to detect the critical path and do performance and latency optimizations. So the critical path is composed of the shortest path from the start of the trace to the end of the trace. So if we were to optimize and speed up all the spans along this critical path, we can reduce the overall latency of the entire distributed transaction. So if you recall the demo that Prithvi gave yesterday, there was a MySQL span in our trace where about 90% of our time was being wasted. So using that information, you could easily have gone in there and optimized that MySQL read by adding like a bigger thread pool, or perhaps even adding a cache in front of it and reducing the overall time spent on that read. So I recall that there was a study at Amazon that said if you were to increase latency by 100 milliseconds, it would cost them 1% of profit. So think of all the money your company could save by using distributed tracing and figuring out where to optimize correctly. So getting back on topic, with some post-processing, we can use this distributed tracing to generate dependency diagrams that allow engineers to better understand the system that they're working on. And finally, distributed tracing provides a generic distributed context propagation functionality, which everything else is built upon. Okay, but you guys knew all that, so let's just take a deeper look at Jaeger. So I'm going to fly through this side because it was here yesterday. So Jaeger is primarily written in Golang, and we have a couple new components in Java. We allow pluggable storage like Cassandra, Elasticsearch, and in-memory storage to persist traces. There is also an ongoing effort to add support for other storage engines. The UI is written in React, and we support many different languages with different clients. We currently support the 8 that you see at the bottom of the screen. Cool. So here's what the architecture looked like in 2017 when we first open sourced the project. So the light gray box on the left side is the host your application is running in. So your application is instrumented with the Open Tracing API, and you use the Jaeger client library as a concrete implementation of that API. So the Jaeger client batches spans and then forwards the spans to the local Jaeger agent over UDP. The Jaeger agent also runs on the same host as your application, but as a separate process. The agent then buffers these spans for all the other applications also running on the same host, and then it forwards all of them to the Jaeger collector, which is the blue box in the middle, over TCP. So we chose to have an agent per host rather than having every client emit spans directly to the Jaeger collectors to reduce the number of incoming connections to the collectors, since the number of applications far outnumber the number of physical hosts. Also, we wanted to take advantage of using UDP to reduce the amount of overhead that the clients have on your application. So speaking of overhead, so this is a common question that I get all the time, so I'm just going to address it here. So how much overhead does tracing actually add to your application? So the answer is, unfortunately, it depends. So if your application has a lot of complex business logic and takes in the order of hundreds of milliseconds to complete, then the overhead from tracing will be negligible compared to the amount of work already being done by your application. However, if your application is super simple and only takes microseconds to finish, then tracing will add a lot more overhead relative to your application. So essentially what I'm trying to get at is that the overhead for tracing is relative to the application. So in my personal opinion, people rarely ask about the overhead of emitting metrics and logs, and I believe tracing is as important as those, so any overhead is justified. But I digress. So we can chat about this after as well. So the collector, which is the blue box in the center of the screen, is in charge of buffering the spans in memory, sanitizing them, and then storing the spans in a data store like Cassandra. We have a separate Jaeger query service, which is on the right side, and that is used to read traces from the data store and then present them to the user through the Jaeger UI. Additionally, Jaeger collectors are in charge of configuration distribution. This means that the sampling probabilities and all other configurations for applications are all stored in the collector and then forwarded to the Jaeger clients via the Jaeger agent. So this is shown as the red arrows in the diagram. So yeah, the red arrows show the control flow. Sorry. Okay. So we also had an Apache Spark job, which did very basic post-processing of our traces, and it generated dependency diagrams. Okay, and this is what the architecture looks like today. There hasn't been much change on the clients and agents. Most of the changes have occurred in the back end. So first of all, our architecture back in 2017, just going back, was all based on, everything was synchronous. This meant that during load spikes, we were not able to keep up with the traffic, and therefore we had to drop and lose data. Right? So we now have an asynchronous ingestion pipeline that allows us to better deal with these load spikes. So essentially, we traded data loss for increased ingestion latency. So we now buffer spans in Kafka and have a separate ingester service that handles writing the actual spans to Cassandra. So in addition, since now we're buffering spans in Kafka, internally at Uber at least, we've been able to run a span processing job in Apache Flink that generates dependency diagrams and extracts other features. Prithvi will be going into more detail about this new asynchronous ingestion pipeline and the new Jaeger streaming pipeline as well. In a bit, sorry. So additionally, we now added support for Jaeger clients to directly submit spans to the collectors over HTTP rather than going through the Jaeger agents. So this feature is super useful for applications that may be deployed to hosts where you can't run the Jaeger agent and you still need a way to get the spans to the collectors. So for example, if your application is running on a user's desktop, emitting spans over HTTP is the only option you have because you can't install the Jaeger agent and run it on their host. Okay, so now let's take a brief look at the model for Jaeger. This is the current data model, and it's based on Apache Thrift. It's written in Apache Thrift. But there's currently ongoing work to move it to protobuf. So the most basic unit of data is the span, which is the big blob right in the middle. It contains start time, duration, logs, and tags. Each span belongs to a trace and is identified by the trace ID. Additionally, each span can have references, which can be used to model causality between spans. So for example, if one span could be a child of another span, this simply means that the child span was initially initiated by the parent span. So we then combine all these spans into something called a batch, which is the structure you see on the left side of the screen. A batch is just a simple collection of spans for the same process. So you can think of a process as a service or an application. The batch data structure is not exposed to the users. It's just used internally as a normalization tool so that we can deduplicate the amount of data we send over the wire. So to break that down a bit, each span in the same batch all are associated with the same process. So rather than duplicating a process for each span, we just have a batch that just contains one process. So great. So now let's say you want to check out Jaeger and run it for yourself. So how do you go about configuring the collectors, the ingesters, and other components? So we use an open source project called Viper, which allows us to configure Jaeger with both command line flags and environment variables. We also support Kubernetes config maps for those of you guys deploying with Kubernetes. So additionally, the UI is highly customizable, and it's all driven by configuration. You can easily adjust the items shown in the UI header, add Google Analytics token to get usage information, and also configure spans with contextual links. So contextual links are a new feature that was contributed by one of our open source users. So as a concrete example of what you can do with it is, let's say you click a log in one of the spans. You can configure it to take you to the logging system at your company, like Kibana, so you can actually search for other related logs. Another example is perhaps you could add a tag to your span with the build version that you're using, and have the contextual link directly link you to the actual build, so you can see the latest changes all from the UI. So this feature has a lot of potential, and we're very interested in seeing what the community can do with it. OK, cool. And so Jaeger also provides some knobs for configuration, for configuring performance. So if you believe that your Cassandra can take more writes, and your collectors are actually your bottleneck, you can either add more collectors, or you can configure the number of workers and the queue size of the individual collectors and extract more performance out of each one of them, rather than adding more hosts, and then increase the throughput this way. Additionally, you can do the same thing at the agent. These are all configurations. So we have configurations at every level of the architecture, so you can easily fine-tune the performance to fit your hardware specifications. These configurations here that we listed are just examples, number of them. But we also have a lot more, and our documentation provides more knobs at your disposal. Yeah. So let's say you're now running Jaeger, and you fine-tuned everything for your exact needs and have it running. How do you observe that it's actually doing the right thing? So we expose metrics, and we are working on creating a generic Grafana dashboard with graphs that we think are representative of Jaeger's health. We provide both a Prometheus and XVAR metrics backend. Additionally, each component in the stack has its own scrapable endpoint for metrics, if you want to do a quick spot check. So for example, you could hit the collector at port 14268, and you can get all the live metrics for the collector. And that is it for me, and Prithvi will take over and go over new features and our roadmap.
Thank you, Juan, for that introduction. So my part of the talk would be composed of the new features, and then we'd go over the roadmap, and then we'd have time for Q&A at the end. So here we go. So one of the things that we've introduced, so all of these new features are out and released. They've been at use at Uber for about a year, some such. And the first one is adaptive sampling. Now, in any given API, any service you're running, you have differences in terms of what traffic hits what endpoint. What that means is a get endpoint for a user might get a lot more traffic than a post endpoint. Now, the problem with this is that sampling works like this. Sampling is a decision to store the trace, and it is taken at the first edge. So whenever the request comes to your application, a sampling decision is made, and this sampling decision is propagated throughout your application. So this is made at the head, and so far it's been made as a constant probability. You might do it. You might say that sample 1 in every 10,000 traces or 10,000 requests. So when you're seeing a distribution like this, meaning one endpoint has a lot more traffic than another endpoint, what ends up happening is that you get a lot more traces for that endpoint that receives more traffic. And the endpoint that receives less traffic has less traces. So you're collecting different amounts of observability data based on the traffic your application is receiving. Adaptive sampling helps with that. So adaptive sampling works by setting a target QPS. So we do some magic. Talk to us to figure out what that magic is. It's essentially a proportional integral differential controller that takes in the target QPS and the sample QPS and dynamically figures out the sampling probability. And this is done fairly quickly, it's updated every minute or so. And it's tunable how quickly you want these updates. And this will lead to a constant sampling rate so that your observability data per endpoint is roughly the same. The next thing that we have introduced is asynchronous ingestion. So this feature essentially puts a Kafka queue between the collectors and the writers. So we are focusing on this part of the architecture right in the middle. So we've added Kafka in between. So what this allows us to do is when we get load spikes of this nature, we just put it into Kafka, and we read out at nearly a constant rate. So if you're running a storage engine like Cassandra, which can only take a limited amount of QPS, in the sense the storage engine itself doesn't have any protection from load spikes, this architecture enables you to control the rate at which you're actually writing to your storage. You can control the amount of ingester instances. You can also separate it out so that you write only some of the spans into Cassandra, or like you can do lots of advanced logic on the receiving end. So as of now, like we split our writes to span writes and to index writes. So these are handled by separate processes, and we tune them independently at Uber. So this is also out and released. The third feature is trace comparisons. So if you recall from the demo yesterday, we have like a timeline view of traces. So we've taken that concept and advanced it a bit, and we have views like this. So here you're looking at comparisons between two different traces. Boxes that are in red are boxes or services which didn't occur in the first trace but are present in the second trace. And on green, sorry, it's vice versa. Red are the services that have been removed, and green are the services that have been added, services and endpoints. So at a glance, when you take two traces, you can compare the shapes of these traces to see that whether there have been any new requests made by your architecture. So in this particular example, we see a lot of green at the bottom, which says that this trace contains new calls that were not made in the previous trace. And this view allows you to visualize that in a really user-friendly manner. Also, the other thing you could do is you could look at trace durations. So instead of looking at just the number of calls that have been added or removed, we can look at the duration differences. Like in this particular case, the highlighted node has an additional 815 milliseconds, and we also do a percentage duration of that. So these are comparison tools for traces. Finally, we also have a Jaeger operator, so it makes your deploys and updates into Kubernetes really easy. So next we go on to the roadmap. So one of the things that I mentioned earlier with adaptive sampling is that the sampling decision is made when a request hits your service. So we want to make it such that this sampling decision is not made at the beginning, but is made at the end. So what this allows us to do is collect all traces and all spans for a given trace, and then decide whether we want to store the trace or not. So instead of making the decision at the beginning and throwing away spans that we do not need, like here we collect all the spans, and then we figure out based on any sort of heuristics. So this is on the roadmap. Data pipeline is something we are using. We haven't yet open sourced it. We use it internally. So data pipeline is just reading spans from Kafka. We sessionize those spans into traces, and then we run algorithms on it to figure out interesting data. So as of now, we do dependency diagrams, and on the roadmap is latency histograms. So if you're interested in a dependency diagram, this is what it looks like for Uber. So we have about 3,000 microservices. So it's a large amount of data, like zoomed out. So another thing we are working on, we have an open pull request for this, and open issue, is the ability to store and retrieve incomplete spans. So in Jaeger's architecture today, spans are only written to storage when they are complete. So if an application is processing something for a very long time, we do not get any observability information from that application until that process is completed. Imagine imagine an application that runs over multiple days and makes requests over multiple days. Now, these sort of workflows don't really show up in the Jaeger UI today until it is complete. And enabling incomplete span support allows us to visualize those as and when they are happening. Finally, we go into this section about project and community. It's mainly a bunch of links. It's fairly simple. Most of our code is in Go. All of the clients are in the specific client languages. The data pipeline is in Java. So we look for 100% test coverage and signed commits. All of this is on our GitHub page, so feel free. And these are useful links. Finally, Q&A. I could also step down on the side if you want to ask me questions on the side. So yeah, we work on, like me and Juan work on Jaeger full time. So any sort of gnarly questions you have, we're happy to answer it.
Can I speak?
Yes.
Hello, test, test. Oh, hi.
Sir. 不好意思，那个我能用中文表达我的问题吗？
Wait, so
是这样子的，那个就是说我们 Adopt 3.0那个东西，现在是
sorry. Oh, sure. Right.
So now you are support like different kind of
Yes.
future. How are you going to let us use that?
So in the future, we're going to provide a new configuration so that you can just use that. Then you just set one target QPS, right? And that target QPS is set for all your services so that all operations will be sampled at that QPS, right? And that's all you have to provide in the future. So it won't be static anymore, it'll be dynamic. But you don't have to provide per service sampling rates.
I just because from your diagram you have like the Jaeger stream, Jaeger ingestion. Most of the time today we talk about a lot of the ingestion. For the streaming, like what's the purpose for that streaming? Because that's a new architecture compared to the old one. So what's that streaming can be used? Like can we do like back and forth to search different streams or something?
I could take that. So the streaming essentially reads from the Kafka topic. And so the data Jaeger output is spans. So it converts spans into traces. A trace is a collection of spans that is only for given request. Now, that is difficult to do in a non-streaming architecture because we do not know when the request completes. So data might still be arriving. So we use the streaming job firstly to convert the spans into traces. And once we do that, we can run any sort of algorithms on that trace itself. So as of now, what we do is do dependencies. So what that means is we compute service A calls service B calls service C, and then we aggregate it. So we get a call count. So we can do things like in 1 hour, how many times did service A call service B? And we can run any sort of heuristic jobs of that nature. You can reset the stream in time, but we haven't yet written any code that does that or makes use of that functionality. Because we are reading from Kafka, you can say read spans from some previous time or any such.
Basically, comprehensive like that is like the video stream. I can go like back and forth to kind of doing some like old information search. I can kind of compare them without going to the database itself, right?
If you really want to, you can, but we don't really do that today because most of the times you're reading from Kafka and you've already written it down. But if your database goes away or it's dead, you can always reset and load it back.
Thank you.
Yeah. Yes.
I just maybe I'm interested in say combining your write part with the UI, and I want to ingest my data like conform with your data format. So is that possible?
Could you repeat the question, please?
I mean, maybe I can produce my own like debug or kind of tracing information, and
yeah.
I do myself to inject those data into Kafka, and then I want to use your, the right part of your UI and also analysis part. So, I just wonder, is that possible?
As long as you write it in the same format, so the format meaning the data model that Juan showed earlier. So as long as you follow that data model and you supply a deserializer, we should be able to do it. So the serialization and deserialization is pluggable. So it's an interface. You can add whatever you want there. And if you are able to write a deserializer, and then you can just put it in whatever format you want. And yeah, the other pipeline should work.
Thank you.
I have a question. I wonder if we can tag the trace with some more tagging feature.
You can tag individual spans. The tags on the span itself, and the collection of spans is a trace. On the trace itself, like I'm not sure what tagging is. Like we don't yet do that. But on the individual spans, you can add as many tags as you want.
Hey, so when you talk about like moving the like sample rate thing to the end of the pipeline,
yeah,
and is there any like new policy you have to decide whether you want to keep the span or not?
Yeah, pretty much. So it's still very much in the alpha sort of like we haven't yet started work on it, but ideally we'd have users determine whatever they want. So any sort of policy. So if you want to do things like store the span if there's an error, or store the span if this service was involved and the latency was greater than 400 milliseconds, or any sort of very fine-grained settings, you should be able to apply that policy. Because how it works is it collects everything, and then the policy is evaluated before storing.
Thank you.
My question is, what's your recommended way to install and deploy Jaeger now? As I know, we have an official Hemjack and a Jaeger operator as well, right? So is there any difference between them, and what is your recommendation?
I would recommend the Jaeger operator. I don't have a reason to recommend it though, but I think that's what most users are using nowadays.
Cool. We're going to step off to the side, and you can come in. You can ask questions. We're going to hang out here for the next 5-10 minutes or so. That's good.
Thank you.